Good afternoon, folks. Just by way of introduction, I'm sure you all noticed the wind turbine there, but behind it is my house, which is a straw bale house with a grass roof. And we've got some solar PV, solar thermal on the roof, small hydro around the back, electric car. I've had electric car since 1998, so I'm a self-confessed eco-loon who tried all the toys. The straw bale house works, by the way, despite the stories about the three little pigs. So basically the history, we put this turbine up, by the way, about 21 years ago, and we changed the blades about 12 years ago, and it had a major refit last year. But other than that, as a 21-year-old turbine, it has withstood the test of time. It's an old proven turbine, nowadays known as SD Wind. But when we put that up, we thought we could do it better ourselves, and we tried to design a wind turbine ourselves, a downwind turbine. I take my hat off to Otto, who succeeded in getting through there, but I didn't. But we did design an electronic controller as part of our wind turbine, and it became popular with other turbine manufacturers. So a basic history, typical system back in the old days, we had these wind inverters, which are the original of the species. The solar inverters we have nowadays are derived from wind inverters and not the other way around. So the turbine was fed into a safety break, a wind interface with a diversion node on it, and it went into an AC grid high inverter. And the power curve to manage the optimum, obviously, as we know, at every RPM, there's an optimum amount of power to harvest from a turbine that it doesn't overspeed, make too much noise, or stall, and to maximize the power extracted. And that was managed inside the inverter. More recently, they introduced a model of the inverter that could do that based not on turbine voltage, but on turbine frequency, which is a much better predictor of the speed of the turbine. The RPM is the frequency of the turbine. The voltage is more variable depending on the loading at a particular moment in time. So that was an improvement. The dump load interfaces used most commonly were hysteresis based. So they switched on at 560 volts or 530 volts, and they switched off 100 volts lower. And what happened typically is you bang in the load, typically a 6 kilowatt load came in on maybe a 3 or 4 kilowatt turbine. And the voltage would drop like a stone to control the turbine and load the turbine, just prevent it from overspeeding. But and it also was to protect the inverter from seeing more than 600 volts. And then it would immediately, as the voltage fell like a stone, the dump load would come off again at 430 volts and back up. And so the voltage would switch on and off at 430, 530 volts. And this brings the electrics in the system, the electrolytic capacitors are charging and discharging. You're putting more wear and tear on the system. It wasn't really ideal. A little bit later on, ABB, or Power One as they were at the time, brought out a wind interface with the pulse width modulated dump load. They also moved the logic for the power curve, the managing of the table of power to be extracted from the inverter at different speeds. The management of that power table was put into the wind interface, and it controlled the inverter through a frequency connection. But with the pulse width modulation on the dump load, you had effectively a dimmer switch that you could control it, that it came on gradually at 430 volts and was at 100% maybe at 500 volts or whatever voltages you were working within. So instead of having a sudden impact of kicking in a major load and dropping the voltage up and down, you were able to be more gradual about how you controlled it. That product was discontinued by ABB, and we introduced our controller, a version of our controller which performed the same functionality. And instead of it sent a frequency signal to the inverter, and again the power table was stored inside the controller, and it managed the inverter externally through a frequency signal, which is quite unusual, but it worked. They then, within about a year, SMA, ABB, and Jinlong all stopped making wind inverters. All three companies are experiencing an absolute boom in the sale of solar PV. So while we were excitedly ordering 3 pallets of inverters, somebody else was on the other phone ordering 15 container loads of solar ones. So all three companies discontinued wind inverters, and you could no longer get a reliable wind inverter with the power table. So we were already in the market for that sort of product. So we developed a controller as before, but instead of using a frequency to tell the inverter how much power to convert, we did it over Modbus. So now the dump load control is done in here. The power curve control is done in here, but it sends a signal to the inverter every 30 times a second saying, give me 10 kilowatts, give me 12 kilowatts, give me 15 kilowatts, give me 10, give me 12, give me 12, give me 10. Very rapidly changing the power conversion so that there was an appropriate load, both in terms of torque on the shaft of the generator and in terms of controlling the generator speed and optimizing power output. So later on, we produced the 40 amp and 30 amp versions for smaller turbines and to fill the market for smaller turbines. We also produced a small DIN rail mounted. This is a unit about 20 centimeters by 20 centimeters. DIN rail mounted, which is just purely the logic chip from the other board for the power curve. So it read the turbine voltage, it read the turbine frequency. It also data logged all of these controllers that we make data log to an SD card every second. All the information on the turbine speed, the turbine voltage, anemometer if you have wind speed, an anemometer. The logs the inverter voltage, the grid frequency, the grid power, and all the fault conditions on the inverter and anything else that's worth saving. And it's great for diagnostics. When something goes wrong, we can pin the tail on the right donkey. So a modern system would have either company's own controller controlling the dump load, or this would be part of our single unit. And this controls the power curve on up to 4 inverters at a time, feeding the grid. So this unit that we do now rectifies the wild AC into DC, and it's got smoothing capacitors to bring the ripple down below 5% for the inverter input. It provides the inverter with DC from the turbine. It overrides the MPPT tracking on the inverter and manages the solar inverter export based on frequency or the voltage of the turbine, and it does this through Modbus. And we've now got a variable dump load, which is pulse width modulated. And we can provide a DC dump load during grid failure, but we can't pulse width modulate it because we don't have power to drive the microprocessor and the drivers. And this is all based on a small printed circuit board, which is standard to all of our units. Sorry, lost the mouse pointer. But anyway, this board goes into a box with, as you see, a heatsink on the side of it. And onto the heatsink, we mount a bridge rectifier in the IGBT. And there's a general purpose relay up here, which can be used to brake the turbine using either a disc brake or changing a linear actuator to change the pitch of the blade. So whatever system the turbine manufacturer is using. It's got an anemometer input here. It's got a general purpose relay. Sorry, I said that already. We're also working on a hydro version of this to optimize for hydro, because hydro doesn't have a standard power curve no matter where you stick a hydro. Different hydros will have different head heights and different flow rates and behave differently. They have cavitation problems. And so we're working on an algorithm to optimize the power table for hydro to make it self-optimizing, which is another trick that we're at. So I kind of covered all that. Oh yeah, another thing that we can do is detect phase loss. It's quite important to detect phase loss, particularly if you're using frequency to control the power conversion by the inverter. Because if you're using frequency, the two wild AC strings that you're connecting the frequency measurement to may be working, but you could lose the third leg. You could tell the inverter to convert 6 kilowatts because you're seeing a frequency of 50 hertz, as you think the turbine is going fast. But if the inverter starts converting power, you start a vibration in the tower and you shake it to bits. So if you're going to use frequency to base your power curve, you need to have some way of knowing if you've lost a phase. So these are the connections on the turbine. There's a micro SD card here, the connection here to connect it to your laptop to program the controller. Input here from Modbus from the anemometer, and also an external Modbus. The controller has its own Modbus for people who want to control or read it remotely. It's got a connection. The wild AC comes in here, goes up here to the rectifier, comes back as DC from the rectifier to here to go to the inverter. The DC comes up here to the IGBT, and the IGBT is connected down here for the DC to the dump load. And the IGBT and the rectifiers are mounted on the heatsink. Over time, because we do our own programming in-house and we have our own coders, I mean, one thing I learned when I was coding myself is there's no such thing as no, it can't be done. It's just how much do you want to pay for it and how badly do you want it. So people come to us with versions of the controller that they want customized, and we sometimes kick ourselves for saying that, but anyway, it is true. So the kind of things we've been asked for is for a PWM version of the dump load. Some people develop a wind turbine, and the test bed site, they have to test it in a remote field, but they don't have a reliable grid connection. So you can actually program the power curve into the controller, and the power curve will behave like an inverter, and it'll obey the power table that you programmed into it. And it stores data on how much power you converted because it knows the resistance of the dump load. Now, it's slightly inaccurate because the dump load resistance changes slightly as it heats up or cools down. So it's not 100% accurate. But we see people who've developed a turbine and they see it spinning at 100 RPM and they see 300 volts on the generator, and they look at the generator and say the generator at 300 volts can deliver 5 kilowatts. So they say they have a 5 kilowatt turbine. Of course, then they put 50 watts of load on so the thing dies a death. And they really don't have a working turbine at all. We see a lot of various stage projects coming in. But it does mean that you can test basic concepts quite early on in the development of the product. All you need is a dump load controller and a dump load resistor. G100 is something that came on in the UK recently, where you had to control your exports. And we can do that through the dump load or through switching on AC loads. So you might have a 10 kilowatt inverter, but you might only be allowed to export 3.6 kilowatts. So if you're getting to the point where you're exporting more than 2 kilowatts, you can switch on a heater to control the export. But we can also bring in a dump load. But here's the neat trick. Other companies can bring in a dump load, or sorry, can reduce the output of the inverter in accordance with G100, which the inverter may even do itself. But that takes the load off the turbine. So now the turbine is slightly overspeeding. And I've seen cases where, for example, there was a turbine, a proven turbine in Ireland that met the noise requirements of the planning permission and the planning consent. But when the neighbour measured the actual noise, it was above the limit, which it could do if there was turbulence. But the other reason it could do it was because there was a grid failure, or if there was a G100 error, that the turbine would overspeed, and then all bets are off as to what noise it will make. So what we do is, if we have 3.6 kilowatts going to the grid as a maximum, and we're exporting 4 kilowatts, we take 400 watts off the inverter feed, but we add 400 watts onto the dump load. So we keep the turbine torque and power conversion, power level as it should be, as it's designed for. Power limiting based on analog. Some people want to be able to just set a power limit with an analog signal from their own controller. We offer that as well. For off-grid systems, Sunny Island and Victron systems will change the frequency of the grid to when the batteries are getting full. And that means that you need to back off your inverter. So we read the frequency of the grid already from the inverter. So we see that the grid frequency has gone over 50, it's gone up to 51 hertz. We know that that's this Victron saying to us, cut back the grid feed from the inverters. So we cut back the grid feed from the inverters. And again, we apply the same amount that we're cutting back on the inverters. We apply it to the dump load resistor so that the torque on the generator is constant, but the Victron system or the Sunny Island system is seeing the appropriate amount of power for the state of the batteries. Again, hysteresis AC load switching is also used for this. We also have another trick we added in was when a turbine cut out because of overspeed or over wind speed being too high. We might want to reintroduce the turbine when the wind is slowed down, but we don't know when that is. So we leave the dump load on 100% and release the short circuit brake on the turbine. We see how quickly it accelerates to 30 RPM. If it gets up to 30 RPM within 2 seconds, you know the wind hasn't died yet. So you put the brake back on again and you wait another 10 minutes and you do this test. So we use the turbine as an anemometer to see if it's safe to switch it back on again. So we have options for temperature monitoring. If somebody wants to put a thermistor into the head of the turbine, we can read that. This is another one that was requested. We have one onboard relay, as you mentioned, but we set room for 7 external relays. We sometimes split the rectifier into three to put 3 controllers in for 100 kilowatt turbines where we can't get to the current limit. And similar systems to put small turbines in parallel or in series. You can also use our anemometer logging to improve the power curve, or to monitor and make sure you have the power curve. I'm always astonished at the number of turbine manufacturers who make changes to the blade of their turbine, but they don't go back and revisit the power curve to see if they're putting the right power curve into the inverter, because they don't have easy tools for doing it. They have to bring the turbine out here to a test site, run an analog, an anemometer. But because we can take an anemometer reading and simultaneously read the anemometer reading and how the turbine is performing, we can experiment with changing the power curve to see if at different speeds it improves or disimproves the performance of the turbine for a variety of wind speeds. And it's quite straightforward to do that. So this is an example of being able to put a power curve into the dump load resistor. This is an example of using pulse width modulation to imitate an inverter power curve. At the moment, we work with ABB inverters, which have been taken over by FEMA in Italy. We use them because they respond very quickly to Modbus commands. We can typically tell the inverter to change its power ratio 30 times a second. So 30 times a second, we can read the speed of the turbine, tell the inverter, look at the power table, tell the inverter how much power to convert, and go back to looking at the speed of the turbine again. So very fast we can do that. It used to be 10 times a second for the wind inverters. But we find it very hard, so we're interested in looking for an inverter manufacturer who can offer that kind of speed, because most of the Chinese inverters, and the German ones like SMA and Fronius, the Modbus response is about 2 seconds, which is too slow for this kind of wind turbine. So if anybody knows of an inverter in that segment that has a very fast Modbus response, we're always looking for that. So this is where you would see an AC coupled system. My own household system is a 24-volt turbine, which, as you know, means that as the turbine spins in low wind speeds, nothing happens until the turbine gets up to about 28 volts, and then it starts pushing power into the batteries. But then it's stuck at the speed. It becomes like an asynchronous turbine in that it is trying to push against the battery voltage. It can't go really fast because it can't get above 30 volts or whatever voltage the batteries are at. Whereas if you use an AC coupled system, the turbine, the PMG, you have the advantage of it being completely a variable speed turbine that can operate at any speed, and you can extract power at whatever speed it is. But you can put that into an AC microgrid that's fed by a Victron or an SMA on the island. And so we have this system then that if this throws out a change to the frequency in the grid, we get to read that in our controller, and we vary the power accordingly. And this is a typical 3-phase system, which you have one inside here, I see. A 3-phase Victron system providing a 3-phase microgrid. And we can feed that with a 3-phase solar inverter, again, working through our controller and dump load system. I think that's all. These are some of the settings. How am I doing for time, by the way? Get the finger out, yeah. Okay, so these are just some of the variable settings that are optional. I'll skip most of them, but the dump load low voltage means that the dump load will come on at 430 volts at 0% and work its way up to 530 volts at 100%. But you might have a start level where you want it to kick in with a 2 kilowatt load, but maybe not a 4 kilowatt load. So if you set this to somewhere around about 100, it would kick in 1/3 of the dump load. It would kick in with the pulse width modulation of 33%. This is where, when there's no grid, whether you like it or not, we can only offer a hysteresis power dump load. Over voltage at 560 volts, the turbine will shut down. In terms of over frequency, if the turbine gets to 28 hertz for more than 25 seconds, or to 30 hertz for more than 2 seconds, it will stop working and time out for 360 seconds. At this point, there's an advanced option where you could change this so that the turbine worked as an anemometer. The anemometer upper limit 40 hertz is 40 meters per second. That triggers an absolute shutdown. The anemometer multiplier depends on what anemometer you're using, what the multiplier is for the frequency from the anemometer. And this is the ability to put in your power table into the controller. You've all seen this before, I'm sure you're sick of it. And this is various monitoring tabs, information available on the monitoring tab from the Modbus of the inverter and the controller. And this is how you get into the advanced functions, but there's an additional manual for that. So I think that's it, really. I think I've used up your time. Thanks very much for listening to me. And if anybody has any questions.
Thanks, Quentin. Is there any question for him? Online audience.
We're going to run a quiz on this later on. Okay, thank you.
Thanks a lot.
Thanks, everyone.
There are no questions. Okay.
Sorry,
so-
quick question. What's the largest power rating that Voltsys is currently working with for wind turbines? Was it 10 kilowatts? I forgot.
Well, typically we work on up to 30 kilowatts with standard products.
30.
If we get above 30 kilowatts, we can use 3 controllers. Putting rectifiers in one instead of using a 3-phase rectifier, we use one diode for each controller to control, because if you put rectifiers in parallel, they don't work in parallel. But so 100 kilowatts is the largest project we've done so far. That's in Korea.
Thank you.
Thank you.